Welcome to the last lecture of chapter 2. It was a relatively long chapter. Today we're going to talk about gas-liquid equilibrium. So this by itself is a chapter in the textbook. But here we brought it in just one lecture. I think what we did in the previous lectures just laid the ground to make the delivery of this lecture easier. So you'll see that it's heavily connected to what we talked about in the first 7 lectures of the chapter. And this is basically a very general topic. You see it like here and there in thermodynamics, in sometimes mass transport and kinetic. It's a very important phenomenon in any kind of two-phase kind of system. So specifically, we're going to talk about open and closed systems. So that's basically the key term for this lecture. Then we're going to quantify the equilibrium expression, and also look at the PC-pH diagram for specifically the carbonate system. So before we talk about today's lecture, it's good to overview what we talked about so far. So the very first lecture of the chapter, we talked about acid base. So I'm going to use this analogy of this coffee mug. So we had some acid, some base in the system. We defined that. We defined, let's say, this is acid, this is base. And also in the following lecture, we try to solve for speciation. So now that I know I have acid, let's say coffee, what are the components of coffee at equilibrium for this closed enclosure? Then the following lecture was, again, talking about algebra, how to solve it, then talking about graphs and some software to use to deal with speciation. But always it was a closed system. Then we talked about titration. Now I add a base, for example, to the system, and then I look at the profile of pH as a function of how much I'm adding. We zoomed in on titration to focus on buffers. For example, the sweetness factor of this mug is what we're interested in, we want to try to make it salty, and then obviously we have to add salt. Then first, we had to get rid of the sweetness coming from sugar that is inside. So that's sort of a delay. We're adding salt, but it's not salty. So that delay was kind of buffer, and we described buffer intensity also. Then we further zoomed in on buffer to talk about alkalinity, which is basically reducing the pH to 4.5. And we had a lot of justification, why 4.5? And we specifically focus on carbonate type alkalinity, and we mentioned that this is basically because the following lecture, which is this lecture, highlights why carbonate. But always, we were dealing with a closed system. So a closed system that this mug as a system is not exchanging materials with the surrounding. But in this lecture, we're going to open it and expose it to the environment. So basically, it will interact in some way with the environment. So this is basically the whole idea of open system that we're going to talk about in this lecture. So to be more specific, we describe closed system so far. And in the closed system, what we had was like a system that was closed. And this is basically the surrounding, something that we described in chapter 1. So this is the surrounding, and this is the system. But the key point here is that the system has energy and heat transfer. With surrounding. But the point was we don't have any mass transfer. So there's no mass transfer. As the name basically suggests, this is a closed system. So closeness, it refers to the mass transport or the mass transfer of any individual species. But this is not an isolated system in terms of energy, so we have energy and heat transfer, which is basically not the topic of this course. So no mass transfer, this has 2 results. So mass, obviously, uh, within the system. Within the system is it doesn't change. And as a result of that, one of the key equations that we were using was basically the mass balance. So we could write total expression, which was basically the mass balance kind of expression. So we had that over and over. That was one of the key equations we were using. For example, for total sodium, for example, was equal to the individual components that contain sodium, or the same thing for carbonate. So that was true for closed system. But when we deal with open system, then it means we have also the mass transfer between the system and the surrounding. So basically going in and out. And it's basically two ways. So here we also have the same heat and energy transfer. So the same same energy and heat. So here, depending on like what kind of exposure we have or what kind of exchange we have, we may lose one or more of the mass balance equations. So we lose one or more mass balance equations. So this is very critical, because if we lose one equation, that means we have one less equation to solve for all the unknowns. Because if you remember, we had n unknowns and n equations, but now we're actually losing one of them, because some of the species, doesn't need to be all, some of the species might leave the system or might be introduced to the system. So that we don't know exactly what's the mass balance, or there's no mass balance for that species when we only talk about the system. So we have to gain something. And what we gain is basically one or more gas-liquid equilibrium expression. So we gain one or more gas-liquid equilibrium expression. And it makes sense. So we lose some equations due to the nature of the system, and then we gain some again due to the new system. And the whole idea of this lecture would be what kind of information we gain when it comes to the gas-liquid equilibrium, basically. So we're looking for specific equations that can replace the mass balance. So again, we can basically solve for speciation. So take your time, read this part, then we're going to talk about the specifics, basically. So it's basically a general description. If we have a system, let's say this mug that has some coffee in it, we might have some gas going from the atmosphere of this room to the coffee. So this would be gas absorption or dissolution of a gas or some gases. Or it could be opposite, some gas going out from the coffee to the environment. And that would be basically volatilization or gas tripping. So that's basically two different, I told you it's like a two ways kind of interaction. So it could be from the gas to the liquid or liquid from the gas. So qualitatively, the tendency, we basically call it volatility. You've heard this here and there probably. It's a tendency of going from the liquid to the gas phase. And depending on whether we have that interaction, is basically we can divide it to open system and closed system. And as you can guess, this is extremely important, this kind of interaction. The most obvious example is probably for biological systems. So when you have, let's say, a system specifically interacting oxygen, then that would be a key element for biological productivity. So we have so many living things in aquatic system, and it's heavily depending on the oxygen, and that oxygen is it's impacted by the interaction of the gas-liquid equilibrium. And sometimes we can write it in the absorption kind of expression, or sometimes it's basically volatilization kind of expression. That means it depends on how we write the reaction. For example, here, I'm talking about oxygen in the aqueous phase in equilibrium with oxygen in the gas phase. So if we go forward with this reaction, it's basically volatilization going from aqueous phase to the gas phase. We could write it in opposite way also. Later, we see that we use specific designation for either we write it in this way or going opposite. So this is a kind of gas that the interaction is impacting biological system. We have also some interaction between the gas phase and the liquid phase, which is not really that important. So we have, let's say, nitrogen, and nitrogen in the aqueous phase when it comes to the nitrogen in the gas phase or vice versa. It really doesn't impact much other systems. So if we bring some nitrogen to the liquid phase, it doesn't do much. So sometimes when you're doing an experimental work in the lab, your system is sensitive to oxygen. So you purge your liquid with nitrogen to get rid of oxygen. So basically the fact that nitrogen is relatively inert in your system, you're using that to get rid of oxygen. So that could be a safe gas to be introduced to your system. So because there are not many following reactions when you introduce nitrogen to the system. But probably the most important one, and the one that aligns with the content of this chapter, is those that can participate in acid-base reaction. So specifically, carbon dioxide. So if we have a solution, aquatic solution, it might exchange between the liquid and gas phase, CO2. So CO2 in the gas phase can be absorbed or desorbed from the solution. The other one is ammonia. So the same thing, ammonia in the gas phase can be absorbed, and also ammonia in the liquid phase. The other one is H2S. And all of them are very similar because upon introduction of that species from the gas phase to the liquid phase, then we're dealing with acid-base speciation. Specifically looking at H2S. So when you have H2S from the gas phase, it is in equilibrium with the aqueous phase. And once you have this in the aqueous phase, it's depending on the pH. I mean, it will be dissociated to the following acid-base reaction, but depending on the pH, we have different progress of the reaction. So this is a weak acid, HS plus H plus, pKa1, and then this could also undergo S2 minus plus H plus, pKa2. So as you see, these reactions are basically triggered by the exposure to the gas phase. So in the first 7 lectures of this chapter, we were manually adding that acid or base to the system, and then we were basically closing it. But now we're exposing to an atmosphere that contains that H2S. The same thing for CO2. So it seems this is the concentration of this guy would dictate the following, the concentration of this one in the aqueous phase would dictate the following reactions, right? But how about the concentration of this one? What are the factors that can contribute to the concentration of H2S in the aqueous phase? Or let's say I have this bottle. I want some CO2 to be dissolved in this bottle. What are the factors that eventually impacts how much CO2 I get here? So, for example, that's the case for some of the drinks that you have, carbonated drinks. What are the factors? How I can get more of this guy from what we've learned in chapter 1 and 2? Exactly. So based on the general reaction information we had from chapter 1, more you got this one, you get more, proportionally you get more of the one in the liquid phase. So the concentration in the gas phase, so this is basically depending on the concentration of the gas phase. But normally the concentration in the gas phase is more common to report it in partial pressure in the gas phase. So partial pressure, it means the pressure of that individual, the contribution of the pressure of that individual species to the overall pressure. So if we have, like, let's say 20% oxygen in this room and it's 1 atmosphere, then the partial pressure of oxygen would be 0.2 atmosphere. So this is basically a partial pressure. What else? So that means only relying on the partial pressure, that means I expose this coffee to H2S and ammonia with the same concentration or with the same partial pressure, then I would get the same amount of ammonia and H2S. What's that? Temperature it does, but something that it's more related to go from here to here. The volume? Okay. So what dictates how much of this guy we get to this guy? That's very technical. Something simpler from the thermodynamic point of view. That's definitely a kinetic / mass transport factor. What's that? Very simple. Something that we talked. What's that? That's this one. What's that? So let's say this is A, this is B. No matter this is gas phase, liquid phase. What dictates how much of A eventually ends up in B? So always the concentration of B over A is a constant. So which was K. So bigger the constant, mean bigger is the progress of the. So you might bring PCO2 of PCO2 the same as H2S, but here the bottleneck to how much you get in the liquid phase would be basically K for this guy, K for this guy. So the K factor is also playing a role on how much you can eventually bring from the gas phase to the liquid phase. So it was 2 factors, P and K, equilibrium expression, that eventually dictates or impacts H2S in the aqueous phase. So later we're going to see that basically it must be a function of partial pressure of the gas and also some factors related to equilibrium expression. So zooming in a little bit, we can talk about specifically, focus more on the interaction between the gas and liquid phase in the context of Henry's and Raoult's region. So here we want to use a model gas, which is basically X. In the aqueous is in equilibrium with X in the gas phase. So I'm writing this reaction in terms of the desorption or volatilization, because I'm going from the liquid phase, the gas is leaving the system, the aqueous system. And if we go to the lab, measure the concentration of in the liquid phase, so basically we can change the concentration in the liquid phase manually. Let's say carbonic acid. We can change different concentration of carbonic acid. And then measure the concentration in the gas phase. So this is what we're measuring in the lab, or measuring the partial pressure of X. Then in general, what we see is basically a graph like this one. So it goes like this. Sorry. And like this one. So this is basically empirical curve. So this is what we observe in the lab. We change this guy. I change the concentration of specific acid in the liquid phase. This is an open system. And then I measure how much of the partial pressure of that acid I have in the headspace. For example, using gas chromatography. And then I put the data. I see it follows this trend in general for all the gases. So this is a very, very good, very informative kind of expression, because if you have this for CO2, then later you go back and then predict if you have this much concentration in the gas phase, in the liquid phase, you expect this much in the gas phase. So very informative kind of graph. But to be more specific, we have two regions in the graph. So this is the first linear region, and this is the second linear region. So the first linear region is basically here. And this is the second linear region. So the linear region, it's the concentration in the liquid phase is linearly connected to the concentration in the gas phase. And linear expression is very useful because basically the concentration of these two are related by a constant, by the slope. So that's why we really like the linear kind of regions. So what it says is that the difference between this region and this region is basically the concentration of that species in the liquid phase. So here the concentration is very small. So it seems there's a tiny amount of acid in this bottle. But here it seems most of the bottle is that acid specifically. So to be more descriptive, we have two linear regions. Specifically, the first region is when the volatile species is very dilute. We call this basically Henry's region. I think this is not perfectly linear, this is linear. And the second part is basically when the concentration is very high, so when the liquid phase is almost pure X. So this is basically Raoult's region. If you took thermodynamics, these are pretty familiar terms to you. In thermodynamics, we deal with both regions, and they are like very important, both. And they represent specific kind of systems. But in the context of environmental system, which region is the important one? Are we dealing with volatile species at low concentration, or are we dealing with volatile species at a very high concentration? Low concentration. So specifically looking at, let's say, ocean, which is one of the main bodies of environmental system, the concentration of CO2 is very low. So X in the aqueous phase, it's 2 millimolar, for example. And that 2 millimolar compared to the whole system is very tiny. So it's very dilute. So most of the environmental system will basically deal with the Henry's region. So in environmental system, so we often deal with the Henry's region. So we're basically narrowing it down to this region. So long story short, the concentration of in the aqueous phase is linearly related to the concentration in the gas phase. And now we're looking for this constant, this slope, because this is basically constant, no matter what kind of specific part of the Henry's region we're dealing with. And that constant is basically Henry's constant. So which correlates the concentration from the gas phase to the liquid phase, or vice versa. So to be more specific, we can focus on Henry's law. Henry's law, we have the standard form of writing a sort of an equation to get to Henry's law, and that's basically in the form of volatilization. So in this form, we go from the aqueous phase to the gas phase. And like any other reactions, we can write down the expression for the equilibrium constant, and that would be the product, in this case, the gas phase concentration to the concentration in the liquid phase. And then for this standard reaction, the interaction between the liquid and the gas phase, written in the volatilization approach, or then we can use a designation of H, special designation for K, which is basically Henry's constant. So Henry's constant, when you see it like in tables, it is always referring to this kind of expression, this kind of reaction, which represent this kind of expression. So it's always the gas phase divided by the liquid phase concentration. But sometimes we deal with absorption kind of expression, which is also the opposite, literally the opposite of this reaction. So we deal with absorption. In this case, we go from gas phase, it's being absorbed, to the liquid phase. Then again, general K expression would be the product over the reactant, which would be 1 over H. So if we define H for the top reaction, then this would basically 1 over H. In this case, sometimes we use special designation of KH. So if you see KH, in the homework, in the exam, it's referring to the absorption type of experiment or the absorption kind of expression. When you see H, which is more common, it's basically talking about volatilization. And I think it's fair to say, in this case, activity is equal to the concentration. So it's safe to express this equilibrium using concentration, because one of the conditions to be inside Henry's region is basically we're dealing with dilute species. It was more on the left side of the spectrum. So it's fair to assume the concentration and activities are equal. So one other important factor is that we can write H, the Henry's constant value, in different expression depending on how we report the concentration for each individual. Because in the gas phase, it could be just a normal concentration, mole per liter. But as I told you, this is not very common for the gas phase. So it's partial pressure, which means it's atmosphere. Or sometimes it is a mass concentration, so milligram per liter. So depending on the units of the gas phase and the liquid phase, we could get different variations of H. And this is basically an important table that eventually tells you what kind of expression we have. So if we use mass concentration for the gas phase and mass concentration for also the liquid phase, then we have the subscript of HCC here, the concentration in terms of mass. HPM is probably the most common one. You have partial pressure in atmosphere for the gas phase, and you have molar concentration in the liquid phase, so HPM. So the unit would be atmosphere per mole per liter, and then you get liter here. So depending on like how this data is given, you have to basically think about what's the unit and how that equilibrium is expressed. And this is another key table when it comes to specific elements. For example, carbon dioxide is probably the most important one. As you see, it is written in HPM, HCC, or HMM. So depending on like what is given or what is asked, you can basically go to this table and then get that value that you're looking for. So this table is extremely important, and that's basically, it tells you how much of the, eventually how much, what's the extent of the interaction between the gas and liquid phase. So one quick question. Carbon monoxide is 1050 compared to, let's say, ammonia, which is 0.01, a huge difference. So which one is more volatile? Why ammonia? So before you look at PM, it's H. It's the factor of volatilization. So that means the gas phase is the product. Exactly. So the gas phase concentration is the denominator divided by the liquid phase. So it shows carbon monoxide is way more volatile. So bringing carbon monoxide to this liquid phase is extremely difficult. But ammonia is pretty fast. So this gives you a sense of like the relative solubility / volatility of different gases. And based on, like, we can play with the units. This is basically a quick example. So you guys think about like what is required here, and then what is basically the concentration for this benzene case that we are dealing with here. So we have a water sample exposed to benzene gas. Obviously, it's an open system. We have the partial pressure. We want to know what's the gas. Eventually, if we leave it for a long time, what's the concentration of benzene in the liquid phase, sorry. So here the partial pressure is given. The concentration in the aqueous phase is requested, right? So this is in atmosphere. This is in mole per liter. So what kind of H we need? What's that? PM, exactly. So we need HPM because that basically simplifies some of the calculations down the road. HPM, we know it's always, because we're using H, not KH, it's always the gas phase. In this case, written in the atmosphere or the partial pressure divided by the concentration of B in the aqueous phase. What is HPM of benzene? Yep, 5.56, and always make sure the unit is correct. So atmosphere per mole per liter. So therefore, concentration of B in the aqueous phase would be 0.9 atmosphere divided by 5.56 atmosphere divided by mole per liter equal to 1.6 10 to the minus 2 mole per liter, or 16 millimolar. So very simple, but very informative. Let's say you're working in a chemical plant. You want to predict if you have this partial pressure of benzene in the atmosphere, in that, let's say, absorption column. Then eventually what would be the concentration in the liquid phase if you let it equilibrate for enough time. That would be dictated by the partial pressure and also the K value. Eventually you get 16 millimolar, bringing it to the liquid phase. So H is similar to any other equilibrium constant. So basically it's temperature dependent. We can look at how temperature is impacting that, basically the H factor. We can write down the expression of the reaction in a volatilization way, again, going from aqueous phase to X of gas. And we know this is described by H, so the concentration of X in the gas phase, concentration in the aqueous phase. And we know basically this is volatilization, or which has delta H 0 of R. So we know we can basically, for any temperature dependent K factor, including H, use Van Hoff. So we have ln T2 to T1. Sorry, that's H basically. H T2 to H T1. This could be delta H R 1 minus 1 T1 and minus T2. So we want to see how H changes if, let's say, we increase the temperature, or how volatile X gets when we increase the temperature. You definitely know the answer, but here we want to mathematically also prove that. So what is the delta H standard of volatilization? Is it exothermic or endothermic? Do you need to apply heat to evaporate, or you consume heat? So you apply heat. So basically it's always positive. It's always endothermic. So it's always positive. Therefore, if this is positive, we know basically T2 is bigger than T1, so we increase the temperature from T2 to T1 to T2. Then this part would be also positive. So for the ln function to be positive, that means that h T2 over ht1 needs to be bigger than 1. Just the ln function. ln function is basically like this. This is 1. Bigger than 1 is positive, smaller than 1 is negative. So this means ht2 bigger than ht1. So this means H is indication of volatility of a gas. When we increase the temperature, it's more volatile. That's what we know for sure, right? And this is basically showing that the factor that indicates that how volatile it is increased for the higher temperature compared to the lower temperature. So volatility always increases with increasing temperature. This is pretty obvious, but we just wanted to put it into the context of this Van Hoff. So that H is a function of temperature, but it's also a function of the solution composition. So if you bring the same gas, which is, let's say, carbon dioxide, the same partial pressure, you expose it to this bottle and to another bottle, eventually you get two different amount of CO2 in the liquid phase. It was the same H, the same partial pressure, but eventually you're getting a different values. And that's basically a solution composition factor. So the solubility is impacted by that. We're not going to go through the derivatives or any quantitative information about that, but that's basically, that also impacts in real world, in practice. So here is showing, as a function of temperature, the salt composition, specifically Cl minus, of different samples of water, and then how much O2 concentration we get. So if we have a sample that has, let's say, 20 gram per liter of Cl minus, which is roughly seawater, in that case, so this blue line, at 25 C, then we roughly get 6 milligram per liter or 6 ppm of dissolved oxygen. But as you know, the dissolved oxygen is normally in the range of 9 ppm. And that's basically, when we talk about 9 ppm, is because we're dealing with no salt, roughly no salt in the solution. So it's roughly here. So we added salt, we kicked out a gas. So this effect is called sometimes salting out of the gas. So if you have a glass of water, and if you have only salt in your hand, the easiest way to get rid of oxygen is just to add some salt. It might kill the fish, but that's basically salting out the gas. So the concentration of dissolved oxygen in seawater is different than like fresh lake, for example. Even though they're exposed to the same gas, the same partial pressure. So the reason is basically this one. This might be a good question for the exam also. So salting out effect. So temperature and salting out effect. So that's basically the two factors. So now let's be a little bit more quantitative, talking about how we can use this Henry's law for solving this speciation. So as I mentioned, this is basically the interaction between gas and liquid phase, specifically those that result in species that has like acid-base kind reaction. It's very important for speciation that we're interested in. And we can basically quantify this. So let's assume we have a gas-liquid equilibrium of CO2. So we have CO2 in the gas phase. Then based on the Henry's law, we get some CO2 in the aqueous phase. And now once we have CO2 in the aqueous phase, then we don't have control on not having the following speciation. We always have it because this is a weak acid. So some textbook, they use aqueous CO2, but some of them, they use carbonic acid in the aqueous phase. Some of them, they also use carbonic acid with star. But eventually what they're trying to describe is the concentration, the total concentration of CO2 that you're bringing to the system by interaction with the gas phase. So here in this course, we're basically using this carbonic acid term, the same as we use for the normal acid-base reaction. So here it seems we're bypassing this guy. We're going from CO2 gas all the way to carbonic acid. But again, some textbook use like different notations, like H plus, something like that. But here we're just basically going from here directly to here. So, and if that's the case, this is not volatilization, this is absorption. So we're not allowed to use H, but rather KH. And KH would be eventually how much we're bringing of the gas to the liquid phase. In this case, we're directly using carbonic acid expression, as I mentioned, compared to CO2 in the gas phase. And now once we have H2CO3 carbonic acid, we have also acid-base reaction. So we have, as always, H2CO3s to bicarbonate. That's basically Ka1 and then bicarbonate to carbonate, and that's Ka2. So it seems they're basically connected. So you get the gas, bring it here, it follows this expression of how much you eventually bring it here. And then when you bring it here, then it follows these two reactions. So it seems they're both connected together. So now we can basically dig deeper on the difference between a closed system and an open system. So in a closed system, what we had before, so let's say this is our closed system, we had mass balance expression. So the mass balance expression was the total CO3. It was equal to the amount that we were initially like adding to the system, for example. And that was H2CO3, HCO3 minus, and then CO3 2 minus. So this is, let's say, initially what we added to this bottle. We close the lid. So the total mass balance is always equal. So if we change the pH for the system without opening it, what would change and what wouldn't change? So we're dealing with 4 terms. What changes if we change the pH for a closed system? Yeah. So if we, let's say hypothetically, I'm changing the pH of the system. Which of these 4 would change? Which one? What changes? Like the direction doesn't matter at this point. Does this change? Yeah, It's a part of acid base, the same as these two. But always the combination of the three, no matter at what pH, would follow the conservation of mass because the system is closed. So in a closed system, so this is a very delicate difference between a closed system and open system. So in the closed system, all the species, including H2CO3, changes with pH. But total is constant. So what I'm doing by changing pH is basically changing the ratio of H2CO3, HCO3 minus, and CO3 minus. For example, if I'm increasing the pH, then I'm getting more of bicarbonate and carbonate, and if I'm reducing pH, I'm protonating it more to be more carbonic acid. But eventually, the overall concentration would be the same. But now when we look at the open system, then we have interaction. So CO2 is going out and coming in. So what is constant here? In the system, not outside. Outside, obviously, the partial pressure of CO2 is constant. So to answer that, let's write down that KH there, which relates the concentration of H2O3 in the aqueous phase divided by CO2 in the gas phase. Let's rearrange this. H2CO3 is KH times so what is constant now? Is this constant? I mean, assuming temperature doesn't change. This is a constant, right? Henry's constant for CO2. How about this guy? The concentration of CO2 in the atmosphere or in the gas phase, assuming that the system is not big enough to take out or take significant amount of that gas to the system. So it's constant. The concentration of CO2 in the gas phase in the atmosphere in this case is constant, roughly 410 ppm. So what we see is basically this expression is constant. It might look a bit weird, but the carbonic acid specific species, the carbonic acid concentration for an open system is basically constant. But that doesn't mean we don't have other acid-base reactions. So this will be also converted to bicarbonate and carbonate. But the concentration of this guy is always constant because it's simple. It's always dictated by the partial pressure and the type of gas. So what changes if the concentration is constant? No, the concentration of H2CO3 and CO2 is constant. If I change the pH, yep. So let's say this is a pH 2 media. I expose it to CO2. It's so acidic, we can qualitatively describe that also, that it doesn't let much CO2 to be absorbed. H2CO3 concentration would be the same, but because it's so acidic, it won't deprotonate to bicarbonate and carbonate. So it stays there. But let's say if this is pH of 11, and you bring bicarbonate or you bring CO2 to expose to this liquid, then the concentration of H2CO3 would be the same, but then it has a lot of room to basically go towards bicarbonate and carbonate. So eventually what you're getting is way more total CO3 at pH 11 compared to pH 3. Again, mathematically we can calculate it, but qualitatively speaking, a more basic solution has more room for acidic gas. So in this case, the total CO3 changes with pH. Again, this might be a little bit confusing, but when we a little bit practice on the quantitative side, you see that basically this is how this is changing, specifically using graphs. So now that's the reason we're not allowed to use mass balance equation, because in the previous case, mass balance is always fixed, is equal to constant. That's one of the good equilibrium. But here we're losing this one, but we're gaining this one. So we should be good in terms of calculating for speciation. So now let's focus on a PC-pH type of diagram and writing the speciation. So now this question is about carbonic acid. Again, the most classic gas when it comes to gas-liquid equilibrium for environmental systems. But later you see that we might have two different gases, three different gases. It's basically the same. As long as they're not interacting with each other in the gas phase, it would be the same concept. Again, it adds more of the species. So here we want to go with PC-pH diagram, lecture 9, very common practice, but now for open system. We know PCO2 is 10 to the minus 3.5 atmosphere. KH is 10 to the minus 1.5. And we know pKa1 and pKa2 for carbonic acid. So now we want to mathematically describe how the profile is changing as a function of pH. So let's first look at the speciation, like what species we have. The same exact practice. What are the species here? In the liquid phase, we really don't care about the gas phase. The gas phase is just a boundary condition. Yep. So H2CO3 obviously in the liquid phase. Yep. Nice. So we have 1, 2, 3, 4, 5. 5 species, we need 5 equations. So in terms of the equations, can we use charge balance? So open system, how does it change charge balance? Charge balance is all about water neutrality. And it's just so much respect for charge balance that we can't even dare to look at it. It's always true. So it's always there. I mean, mass balance, obviously, because we're focusing on the system, we can ignore mass balance. But for example, if the system was the universe, then it would be the first law of thermodynamics. But anyway, the charge balance is always there. It's a charge balance. So we can do charge balance on the system. It's H plus equal to OH minus plus HCO3 minus plus 2 times CO3 2 minus. Again, this is charge balance, so it cares about the charge itself. So this is 1. Now we can do equilibriums. The first equilibrium is KWH plus OH minus, so same plus 1. Then the first one is Ka1 of acid, HCO3 minus H plus, H2CO3, and Ka2 is HCO3, CO3 2 minus H plus, and then divided by HCO3 minus. So now that's 4 normally for closed system. The fifth one, or the order really doesn't matter. The one that we use is mass balance, but here we're not allowed to use mass balance. Rather, we use that KH expression because we have all the information that we need to calculate. and CO2 gas. This would be our fifth. So from here, to construct the graph is basically all lecture 9. We're interested to look at PC, pH. So that means we're interested to convert every concentration to the P form. So if we have concentration of H2CO3, we're interested to know about minus log of that concentration to be able to use that PC-pH curve. So the easiest here is so we need 5 lines, 5 equations of the line which has PC, that C represent one of the 5 species, and pH as the x-axis. So the easiest is to work with H2CO3 line. So basically it's line 5. In line 5, if I rearrange it, H2CO3 would be KH times CO2 gas. So here, I just need to do minus log of each side. So it would be basically minus log of each side. Then it would be minus log of H2CO3 equal to minus log of KH plus minus log of CO2 concentration in the gas phase. So then this would be PH2CO3 minus log of KH. KH is a constant, so this is KH, this is the value. The log would be minus 1.5, so minus log would be 1.5. So when we look at the unit for KH is in the atmosphere. So basically this is also in the form of atmosphere, so we don't really need to convert that. Minus log of the concentration of CO2 in the atmosphere version, this would be 3.5. So that's basically one line. The concentration of H2CO3 at any pH is equal to 5. I mean, minus log of that. So the concentration itself is always 10 to the minus 5, no matter what the pH is. As mentioned, this is basically true for open systems. So again, if we have any question about how we're doing this, lecture 9 would be a good reference. So the rest would be pretty straightforward. HCO3 minus, we use equation 3, then it would be HCO3 minus, it would be equal to Ka1 H2CO3 divided by H plus. Then if we do minus log and then do all the conversion, then it would be PHCO3 minus equal to P of Ka1, which is 6.3, P of this guy, which would be equal to 5, as we calculated, minus pH, which would be basically that pH term. So here is the equation for the line for H2CO3, HCO3 minus. So this is the first line, this is the second line. So you have the expression, you mathematically play with it to get into that P form. So the third one would be CO3 2 minus. We use equation 4, which is CO3 2 minus, rearrange it, Ka2 HCO3 minus that we just calculated divided by H plus. Again, minus log. In the form of P, then there would be PCO3 2 minus equal to pK A2 10 to the power 10.3 plus P of HCO3, which is coming from the last page. So that was, we just calculated to be equal to this guy, minus pH, so which is in the denominator here. So this one, we got it from the previous page. Rearranging a little bit, then PCO3 2 minus was 21.6 minus 2 pH. So that's the third line in our graph representing CO3 carbonate. And the last two would be basically H plus and OH minus. And this is exactly as described before. Basically two simple lines. This was lecture 9. And now the total concentration, because that the total concentration is not a constant, we can also have a line which was a constant in all closed system. Also we define H2CO3 plus HCO3 minus plus CO3 2 minus. Okay, because this is a mass balance, there is no 2 factor here. That was just for the charge balance. So we have 5 species and 5 lines. So then it would be, I think, very straightforward to construct the line, right? The first line and the easiest line is always H plus OH minus. So I'm going to do H plus first. So this is H plus, similar to lecture 9. This is OH minus. So I'll be providing these 2 figures also in the on Teams. So if you have a little bit of problem constructing that. So the next one would be basically H2CO3, always equal to 5, right? So that would be this line the whole time. It's not pH dependent. So this is H2CO3, not a pH dependent line. The next line is bicarbonate, HCO3 minus. We need to look at the equation of the line. This was the equation. Well, I didn't simplify this, so this has to be basically simplified to a better form. Sorry. So then it would be PHCO3 minus 11.3 minus pH. So this is the equation for the line. 2 points you need to construct the line. 1 point would be pH of 0. pH of 0, then PCO3 would be 11.3. So pH of 0, then this would be 11.3 here. So 11.3. And then we're looking for a value that PC gets to 0, just 2 points. Then we're looking at the equation. If this guy wants to be 0, then pH is also 11.3. So then would be 11.3 here, roughly. And then obviously the slope is also 1 because it's minus pH. The slope is basically minus 1. And it's parallel to this line. So this is for HCO3 minus. So the last line is this guy. We know the slope is -2, and then we just put two values to get to the line itself. Let's say I put pH of 10. So pH of 10, this would be 1.6 eventually. So 1.6 pH of 10, so it would be here. And then the other one would be, what's the pH of, at what pH this guy gets to 0. So I'll just have the interception here. So it would be 10.8, right? Roughly near 11. Again, like you can pick whatever 2 points you like. You have the equations for the line, so it would be pretty straightforward. CO3 2 minus. So now this is all the lines representing the system. At any pH, you can predict what are the species concentration. For example, at pH 8, I know this is the concentration of H+, this is the concentration of OH-, this is the concentration of carbonate, H2CO3, and bicarbonate. As always, like for open system, this is constant, it's not pH dependent. So now the last line is the total line. And if you remember from lecture 9, when it comes to combining three lines in this P type of graph, is you get the maximum one for each point. So let's trace from here to here. We get the maximum between the three green colors. Okay? So before that, let me just copy this one because I need this. Okay, so the maximum. So starting from here, you see that it's this guy dominant. So this, out of these three lines, this is the maximum value. And then when we get to this part, this is a bigger value. And when we get to this part, this is the bigger value. So this is the more dominant species impacting the overall. So it would be this one, then this one, and this one. So that is the total CO3 line. So as you see, the total value is increasing. More alkaline solution, you bring more of the acid gas to the system. So you absorb more. So if you want to desorb CO2, you basically reduce the pH. So the next part is simply asking for, now we have this graph, what is the pH? Because if you expose this water to this partial pressure of CO2, eventually it gets to a pH, which as we're expecting, it should be lower than 7, because this is an acidic gas. So to do that, if we have the graph, we basically, what we can do is using that LHS, RHS technique that we talked about in lecture 9. So, but to do that, we need to figure out what is LHS, what is RHS for this specific charge balance. If we look at the charge balance equation, so we see that for the charge balance, the left-hand side of charge balance is only H+, and the right-hand side of the charge balance is equal to OH- plus HCO3- plus 2 CO3 2-. So this 2 factor makes it a little bit interesting. So this one is pretty straightforward. P of LHS is equal to P of H plus, that's basically this line, Here, P of RHS is equal to the line associated for OH minus plus the line for HCO3 minus. But now we can decouple these two. So it would be plus P of 2 plus P of CO3 2 minus. Again, this was from lecture 9. And P of 2, this is basically minus log of 2. Its value is minus 0.3. So from the combination of the line point of view, you need to combine OH line, HCO3 line, and CO3 2 minus line, then subtract minus 0.3. Subtract in this kind of representation on the y-axis means going up because this is a reverse going from 0 to 14. So we need to combine this line, and these lines. So these three lines, and the combination shifting a little bit, that would be minus 0.3. Okay, and then at the point that this guy is equal to this line, the intersection of the two lines would be the pH, again, lecture 9. So let's do the left-hand side first, which is easier, would be equal to this point. So this is our left-hand side, or the P in the P world, so this would be the P of left-hand side. So the right-hand side, I have to start from the left, take the bigger value, and then increase it by minus 0.3. So the bigger value from the left between these three would be first this guy, and then this guy, right? The bigger value. So now I just need to move it by minus 0.3. So this would be roughly so this is minus 0.3, and this would be right hand side, and this is the intersection, and which is basically the pH of the solution. So pH is where the left hand side is equal to the right hand side. That's basically pH of roughly 5.5. So exposed to acidic gas, yeah. Yep. Up, yeah. So it's minus this factor, or like the combination. So this one plus this one plus this one, which is minus 0.3, plus this one. That's to get rid of that 2 factor in the equation. So again, this might be a little bit confusing, but if you do a little bit of practice and you have a bunch of questions in the problem set, and also an additional question that is solved, fully solved, in the same folder as the main lecture. So you can find that for 2 gases at the same time. So as we saw, this is basically some sort of acidic gas. When we have that interaction with the liquid phase, it changes as a function of partial pressure. It can reduce the pH or increase the pH, basically, depending on the pKa value and also the partial pressure. Some gases, they started to be more effective at the lower pH, at the lower partial pressure, compared to, for example, CO2. SO2 is way more acidic, and that's because basically the pKa is different, and also the partial pressure, and also the H factor. So here's again a typical curve on how the pH would change if we expose that liquid to a different partial pressure of different gases. So this would be the pH. So here we did for SO2, the pH was roughly 5.5. So this was basically that partial pressure we were dealing with. So you can also do it solve it in Mintech. Just on the top part, there's like this gas tab. So when you click on the gas tab, you can specify the gas specifically. And because most of the system are based on equilibrium with like atmosphere, which contains CO2, it's pre-default as CO2 partial pressure. So you can specify other gases, but it would be basically the same. You need the partial pressure, and also you need some other information, but the partial pressure is the one that we described here. So Mintech also can be used very effectively. So to wrap up this lecture, we talked about an open system. For an open system, we basically have CO2 in the aqueous form, or that bicarbonate or carbonic acid, sorry. And then it's interacting with the gas phase, or this is basically H2CO3, and the following reaction in the liquid phase happens after the exposure to the gas phase. So total CO3 is not constant. And this is basically a pH dependent factor. But what we know for sure is the relationship between the species in the gas phase and also the species in the aqueous phase, dictated by the Henry's constant. So as you saw in this lecture, we only solved for one gas in the atmosphere that can interact with the liquid phase. But as you see, this can be applied to more than one gas. So in the folder of the lecture, you have this example, which is basically gas-liquid equilibrium of two gases, H2S and CO2, both in the atmosphere of that liquid, and then the following interaction, and both of them are acidic gases. So you have the whole solution, and then eventually the speciation. So this is the total of CO2 in the liquid phase, and this is for H2S. And as you see, this is basically pH dependent.